I'm a professor of mechanical and industrial engineering here, and it's my great privilege to welcome Dr. Jock Mackinlay, who's our visitor for today and our speaker. And I'm going to start off by just with two quick anecdotes. The first is that I first came across Jock's work when I was working on a book back in the late 80s, and I came across his dissertation. And I have to say that it was groundbreaking, and it had a huge impact on me. And it was the only dissertation I've probably ever read that I wanted to read. All the rest I read because I had to. And then the other memory is, I think it was in 1990 when there was a CHI conference, and I want to say it was in New Orleans. And Jock and the group from Xerox PARC did a workshop on information visualization. And it was like a complete eye-opener for me. And I kind of felt like the guy who commented on Sweet Judy Blue Eyes by Stephen Stills when he first heard it and said, what planet is that guy from? So I've been a huge fan for years, and it's such a great honor. And Jock, we look forward to hearing about your work and your interest. And you've done a great job, not just at Xerox PARC, but also at Tableau. Thank you.
Good. Thank you very much, Mark. I'm going to go to my screen share. Let's try and do that. That should show my slides. And let's see, let's go into presenter view. Everything look good? Wait.
Yep, we can see it all.
There we go. Okay, awesome. Let me see if I can move that up there. That's awesome. Okay, yes. So today I'm going to talk about analytical conversations. And they use data to drive progress on problems both big and small. I'm going to talk about two types of analytical conversations. The first is with individuals having conversations with their computers to understand data, and then people with each other to address problems. There's too much to talk about on this topic, but I'm going to focus down and talk specifically about how encoding data visually supports both types of conversations. Let me start with some examples of big problems, and let me get it so my mouse, my keyboard advances. So these are this is what I mean by big problems: the climate, public health, education, injustice. These are obviously extremely daunting problems. They obviously really, like, to even make progress on them at all, it requires conversation back and forth between people and the use of data during those conversations. But there's a challenge about the use of data, which is that actually it's really hard for people to work with data. So, for example, here's a really simple problem. Here's a 2x2 multiplication problem, and humans have a limited short-term memory. And so if you're going to work this problem in your head, it's actually pretty hard to hold on to the partial results. But humans evolved to be able to use the external world to work with data. And if you put the partial results out down on a piece of paper, you can work this problem much more quickly. And in fact, if you measure people working these problems mentally or by paper, it's 5 times faster. And this is a good example of why visual encoding of data is really, really useful. It's much easier for you all to see that 5 times speed up with the data encoded in bar charts. Now, the issue is that since working with data is really hard, it really is it's really necessary to have it be a team of people who, particularly on the really big problems, are working with it. And this is my sort of emotional image of what it takes in organizations from a team point of view. The ocean down at the bottom represents the bulk of the organization, who we might call data consumers, and they find the data relevant to their work, they consume it, they share the data with each other, they come to decisions, and from those decisions they act on things to make progress. The clouds up at the top represent the skilled people in organizations. There are people who have data skills. They curate the data for the organization. They author, typically nowadays, dashboards to share, to be consumed by people. They model, the people with skills in statistics and machine learning do various modeling of little black or semi-transparent boxes that can be used in the organization, and they generally manage the use of data in their organization. And of course, this image has this water funnel in the middle, and this is I label that water funnel as self-service analysis, self-service analysis is the driver that drives this machine inside of an organization. In particular, the skilled people in the organization, they author their dashboards where people consume them. And people who consume data, sometimes they see something in their data. This is where the self-service comes from. And they see something that leads to a question, and then they start to use their data to try and answer the question. And they can either do that themselves, or they can reach out to one of the more skilled people. And this is the core engine that drives analytical conversations inside of the organization. Now, this lion in the grass, you all immediately saw, because our remote ancestors evolved to be able, to have powerful visual systems that monitor the world. And furthermore, humans have evolved to be able to leap rapidly to decision making based upon their visual system. And so this is why for analytical conversations, visually encoded data is really, really important. Years ago, I was involved with a group of people at Xerox PARC where we went and studied a lot of different people using a lot of different technologies for working with data. And what we found was what we now call, for data work, the cycle of visual analysis. And this is the cycle here. It starts with a task where data is relevant, and almost every task these days, not only is data relevant to it, but there is probably some data that you can find. So you go off and get the data for the task. You choose a visual mapping to tap the power of your visual system. You view the data, you develop an insight, and then you go off and act. Now, when we studied people using lots of different types of technologies, we found out that this is actually a very complex backtracking process and extremely rich. So you start with a task, you get the data. When you choose a visual mapping and you look at the data, almost never is that initial view lead to an insight. You need additional views, so you backtrack to there. Sometimes you realize when you look at your data that you have the wrong data. Sometimes you realize you need more data, so you backtrack to getting more data. Sometimes you realize that what you thought was your task isn't your task, and you change your task. And what's really interesting about the cycle of visual analysis is that even if you get to an insight, then and you validate it, then you need to go off and act on it. But almost always that involves telling other people about your insight. Notice the share under here. And to do effective sharing of a data insight, you almost always need additional visual encodings of the data. Sometimes you need additional data as well to do that. So even from the ACT part of the cycle of visual analysis is there's backtracking. Now, what I want to do, even over Zoom, is I want to illustrate what this cycle of visual analysis for you. And to do that, I want to invoke in you an analytical task so that you can sort of travel along with me on that. And I have a way that I think works over Zoom, and that goes like this. What happens when you have one of these and it meets one of these? If you're super, super lucky, you get one of these. And this, of course, was when Captain Sully hit a flock of birds and was able to successfully land his US Airways plane on the Hudson. And this is called the miracle of the Hudson. All lives were saved. And the obvious analytical task is it safe to fly? And this is what, immediately when I started to see the press about this particular bird strike, that was the question. And somebody at Tableau went off and found out that the FAA, which is the agency of the US government for Federal Aviation Administration, has a wildlife strike mitigation working group, and they've been collecting reports from pilots about wildlife strikes. So you could use this data to answer the question, is it safe to fly? And this is typical data that you see all the time. You have a time column, so flight date. You have string columns like airport and species, and quantitative columns like height and speed. And the issue is, of course, a couple of issues is, when you have a table of data like this, first of all, it's hard to work with this data because humans have trouble with their short-term memory and they have to do mental math here. Also, notice the raggedness along the bottom here. There's actually a fair amount of data here. So it's hard to get in your head all at once. And so what I'm going to do is I'm going to show you how to work with this data using Tableau. And so here's the data in Tableau. It has more columns also than you would see. So there's information about aircraft, airport, conditions, effect, location, the when, and even some information about the wildlife, and then quantitative columns like cost, feet above ground, and the number of strikes. And Tableau, many of you have probably played with it, as you know, is a simple drag and drop interface. And so if I drag out the number of strikes, then you see a bar chart here, and you can see that there, in this particular data set from the FAA, there's almost 300,000 reports from pilots about wildlife strikes. And for this particular question, the amount of damage field is a natural one, absolutely natural one to drag out. And if you drop that on the row shelf, then you break the bar apart, and you can also drop the amount of damage on the color shelf. And what you see here is almost 72,000 reports of null. And what null means is the pilot didn't enter in any damage, and so probably no damage. 140,000 none, all the way down to 143 planes destroyed. And of course, when you have a simple drag and drop interface like this, you can sort of get little subtasks. And so, for example, here's the cost field, and you might want to understand what's the relationship between the number of strikes and the cost. And you can drag and drop that on the column shelf, and you get two columns. Edward Tufte calls these small multiple views because it shares the same axis over here. What you're seeing, of course, is inverse correlation. The count is dropping, whereas the cost is going up. And it's not surprising the cost is going up because this is increased damage. But what was a little surprising to me when I first looked at this data is the size of that orange bar for substantial If you look at on the tooltip, that's $500 million of damage. And so no wonder the FAA has a wildlife strike mitigation working group. So you might already think that it's safe to fly because of the small number of planes that are destroyed. But when you have an easy tool like this, you can then dive in a little deeper to look for to validate whether you're actually seeing the proper signal in the data. And of course, even elementary school students are taught the sort of what, where, when, and why of analytics. And so we can go explore the where and the when for this particular data. And to do that, I'm going to make a new sheet to do that exploration. So for where questions, the state field here is an obvious one. And if you drop the state field on the detail, then you get a map in Tableau, and you can take the number of strikes here and drop it on color, and you get this nice filled map. And actually, since I'm giving a talk in Canada, I'll also drop the origin state. So it turns out that Canadian pilots do report to the FAA, the United States governmental agency, their bird strikes typically when they're actually flying down in the United States. So this is not all of the bird strikes in Canada. But what you can see here is that California, Texas, and Florida are a pretty dark blue, which represents a lot of reports from pilots. And that's not surprising since these are very populous states with lots of pilots. But Colorado is somewhat surprising, although it's sort of blue here. But what I'll tell you as an expert is that color is not a great way to look at quantitative data. But if I pick up the strikes and drop it instead, encode it instead on size, yeah, humans are really actually pretty good at size judgments. And there's a lot of strikes reported from Colorado. And this makes sense if you know Colorado. First of all, commercial flights land in Colorado between the coasts. And second of all, there's a lot of birds that migrate through Colorado. Luckily, where I live here in Washington State, there aren't that many bird strikes. I could dive in, do more statistical analysis, but I'm going to go on to the when question. And that starts basically the same way you saw, drag out the number of strikes. And then I go off and find the obvious date field for a when question. And then I drop that on columns. And you instantly get this trend line here. And there are two things very salient about this line. It's the growth over 2 decades and the drop here on the final year. And when I am live with an audience, I ask people for, why this drop? And almost always somebody in the audience knows that this is data aggregated up at the year level, and this drop is because it's an incomplete year. And you can validate that by drilling down to quarter and changing from quarter to month. And what you're seeing here is for each year, more reports in the summertime and wintertime. And then if you scroll over to the final year, you'll see that this is only September, so it's an incomplete year. And there's also a lag in the amount of reporting that comes in from the previous months. And so that explains this salient feature. And in Tableau, we like to let you directly interact with data, and there's an exclude filter affordance on the tooltip, so I can get rid of that. Then there's this 2-decade-long growth, and when I'm interactive with an audience, I ask for hypotheses about why, and I hear 2 very common ones. One of them is more reporting and more flights, and then when I prompt for a little bit, I hear about more birds. Unfortunately, I don't have a bird population database, but experts have told me that's okay. bird population has been declining because of the climate crisis. So that hypothesis is not there. But for the more reporting and the more flights, we can explore that here. The more reporting is really easy. You saw me do the operation already, where I drop the amount of damage on color, and what you see is the null is going up, the none is going up, but minor, medium, substantial, and destroyed are all staying flat. In other words, where it matters, where there was an actual damage, the reporting has already happened, but the null and the none is going up. And furthermore, there's this little spike here from 2008 to 2009. This was when the miracle on the Hudson happened. So this was obviously that all the press about that encouraged more reporting to happen there. Now, for the more flights one, well, I happen to have a different data set here also from the FAA, which they have been collecting about on-time arrival statistics. And this particular data set has, destination, origin, flight date, flight number, and then a bunch of quantitative values like arrival delay and on like that, and including the number of flights. And so I can drag out the number of flights. That would be the natural thing to do with this data set. This one is a larger data set than the strikes data set. This is 168 million flights. This is commercial flights every day for a bunch of time. And 168 million is enough data that back in the 10 years ago, I would have had to put this into a hot data computation engine like a Microsoft SQL Server or something like that. But I now literally have running on my laptop here a cool columnar database called Hyper that allows this drop. I'm going to pick up flight date and aggregate this data at the year level. And notice how quickly it does that. Super cool. That maintains my ability to have a conversation with the computer. We know that this drop here is an incomplete year, so I'll exclude that. Here's a very salient feature, a drop from 2001 to 2002, and here's a drop starting in 2007. When I interrogate audiences about this, people pretty quickly get that this was because of 9/11, and then this one was the recession, and you can see that also by re-aggregating this data down at the month level, and so cool that happens that quickly. So this is September 2001, and so you can see that. That was 9/11, and it took a while for the flights to recover. And this is August 2008, and this was when Lehman went bankrupt, and a lot of companies stopped their employees flying, and we have basically not recovered since then. But we digress a little bit. I'm going to go back to the full year and use and validate whether this data is driving the strike data. And notice that there's this little linking icon here on flight date. And what because they're both named the same, those two columns are named the same. And what that allows me to do is to drag out the number of strikes and combine them visually with the number of flights. Even though the underlying data is very, very different, I can combine them visually here. And this growth here might have correlated with the flights growth, but over 2 decades, you can clearly see that the number of flights stayed flat while the number of strikes was growing. So that's what I mean by visual analysis, and that's that I hope gives you a feel for what the cycle of visual analysis is. Now, one of the values of technology like that for being able to work effectively with data is that you can get insights. And I hope you learned something about wildlife strikes and whatnot, and you can learn even more. But the real value that technology that supports analytical conversations with computers is that it saves you time. In particular, it can save the skilled people in the organization. It can shorten their projects from many months down to a month or even a few weeks. The other way it can save you time is that for a data consumer, a person who's just using data in their job, they might do a little bit of analytical work on the data rather than just going with their gut decision. And sometimes a person's gut is right, and sometimes it's wrong. And data can be very valuable with protecting us against our biases. So now I want to deep dive a little bit into, as I said at the beginning, into visually encoding data as one part of this conversation with computer. And so what I'm going to do is I'm going to take the psychovisual analysis here, and I'm going to unwrap this into what we call the reference model for visualization. This reference model we developed this in a book called The Readings in Information Visualization to describe all of the papers in the book, and actually a whole bunch of other papers as well. And so this reference model is also sort of described as a pipeline of visualization. So it starts over here on the left with a person who has some tasks, and the pipeline proceeds forward. There's raw data that goes through data transformations, typically into data tables. The data tables are visually mapped into views, and then a person can transform those views to get to understanding. And so this model is very general. And what I'm going to do for this talk is I'm going to focus in on exactly this mapping from data to view, because it's this mapping that taps the human perceptual system. And I'm going to start with a famous book, The Semiology of Graphics by Jacques Bertin, 1967. Jacques had a very trained eye and was very good at encoding data visually. And after a long career of including consultancy and being a professor, he wrote this book. And in this book, he describes a graphical vocabulary. And so this is why there's really a linguistic aspect to visually encoding data. It's actually a vocabulary where there are marks and there are properties for encoding data. And the marks are points, lines, and areas. The most important property is position. Of course, the two most common ways of positioning marks are Cartesian and polar. And then Jock used their additional properties, and he identified specifically these six. He called them retinal properties because the retina of the eye is sensitive to them, independent of their position, color, size, shape, gray level, orientation, and texture. And the cool thing is we have neural machinery for processing these. And so they can be, if you encode data with them, it can be used very effectively. So I built on top of Bertin's work. And of course, I was a computer science PhD student at Stanford. So here's my PhD dissertation. And what I set out to do was to automatically design graphical presentations. And so it was, I wanted the computer to be able to, do this kind of work, because not everyone is skilled at visual presentations. So here's page page 35 in my dissertation, and you can really see the linguistic influence of Bertin's here. So up at the top here is a horizontal position sentence. And in particular, this is where I connected this to bases. After all, as a computer scientist. So here's a database relationship, in particular, a relationship between called price between car and currency. And then down here, I was using logic programming is a predicate in logic. This is where the phrase encodes comes from. I happened to choose that as the predicate in logic. So this describes the connections here between these marks and the axis. I also sort of codified Bertin a little bit more and came up with a composition algebra, which had 3 basic operators: a single axis, double axis, and mark composition, which I could then use to build software to do graphical design. I don't have time to go into details about that, but this work was then picked up and led to Tableau. And in particular, Chris Stolte, also at Stanford, did a dissertation that used my dissertation. And actually, I ended up on Chris's dissertation committee. And these are the 3 founders of Tableau. Chris is the guy in the middle. The CEO was Christian Chabot. And then the person on the right is Pat Hanrahan. Pat is still a full professor at Stanford. He's extremely skilled at all things computer graphics. And what Chris's dissertation did was it combined together computer graphics, computer-human interaction, and databases. Chris had much more chops in databases than I did. And of course, Pat was an expert on computer graphics, and Chris is very skilled in human-computer interaction. So I show these arrows coming together. Think of this as these arrows hitting each other and then an explosion back outward that ultimately led to Tableau. So the core of Tableau, or core of Chris's dissertation, was a specification in a domain-specific language that led to a sort of a cycle of visual analysis or a feedback loop that allowed people to have conversations with their computer. So that specification would result in queries to the database, visual gathering up of the data, a graphical view, and then you would go around the cycle again. And of course, you've seen me demo this. And so I'm going to drill in specifically on this domain-specific language, which we call VizQL. And just as a parenthetical remark, Pat Hanrahan is a world-class expert in domain-specific languages. He was an early employee at Pixar and did the Renderman language there and has a couple Academy Awards for that work as well. So here's a depiction of the domain-specific language that drives the experience that you already saw. So if you put number of strikes on the row shelf, this is the statement in the domain-specific language, and then you generate this graphical view. If you instead put a categorical field on there, you get this view here, start of a table, and that's because this particular domain-specific language has knowledge about essentially the typing of database fields. So, it distinguishes between categorical and quantitative, and then nominal, ordinal, temporal, geographic, et cetera. Those sorts of distinctions. If you put 2 fields on the shells, you get this. You get what you already saw in my demo, and here is the VizQL expression for that. Now, what's interesting about this is that notice that I don't mention bar here. Now, you can say in the domain-specific language that you want it to be a bar chart or another mark type, But there's rules built into the domain-specific language about what type of mark to use if you don't specify it. That's one of the powers of a domain-specific language. And and VisQL has knowledge about tables, Gantt charts, graphs, maps, scatter plots, and dot plots. And these are the basic building blocks for a lot of visual exploration of data. And so, by dropping different fields on the row and column shelf, you can get different types of fields. This algebra also includes algebraic operators. So, for example, the plus operator here gets to small multiple tables where you can have multiple columns, and there's also the cross operator here, which it allows for nesting of values as well. Now, in addition to one of the benefits of VisQL domain-specific language is that it can be compiled into database queries. And since a lot of the valuable data in the world is in databases, this was one of the reasons why Tableau ended up being commercially viable. And so, for example, if you have these fields on the columns and that VisQL expression, then this gets compiled into that piece of SQL over there. Here are different fields, and you get even more SQL. And in fact, you can build up rather incrementally really large chunks of SQL. This is even modest by what Tableau can do. And what that does is it creates it allows people to connect the data and then explore data visually. And the user interface part of the innovation is that you get immediate feedback and incremental construction. So you can start simply, and then you can build up sort. There was sort. You can manipulate filters. You can richly dive deep into your conversation. And we also use, this is another HCI. We have very smart defaults so that people can maintain their flow of visual analysis. So that was my deep dive into visual encoding. I want to remind you that the reference model has other parts. There's the transformation of data into data tables, and I could talk about that. There's also more interaction that you can do. I could talk about that, but I don't have time to do all that. Delighted to do that offline with you. There's a lot to talk about here. But what I'm going to do is I'm going to wrap up the reference model back into the cycle of visual analysis, because this is a talk about analytical conversations. And I want to go to the act part here, the share part. This is where you're not having a conversation with the computer, you're having conversations with each other. And this is particularly important for working on the really big problems. And what I'm going to do is point you to and give you as a reference a book by Hans Rosling called Factfulness. And this is a really fabulous book if you're wanting to try and understand how to have conversations with each other, which after all drive progress on the big problems. Hans was a Swedish trained doctor who went off to Africa and discovered that the world was very different than he had learned in school. And he then gathered up a bunch of UN data. And in particular, he argued that the world was much richer than you might think, that every place has rich and poor, and that there is no gap in all those different places. This is a picture of him at a Tableau customer conference that I got to attend in London. He was really good at telling stories with data. He had this amazing pointer here for pointing at things, and he's using the Socratic method to help people sort of dive into his data. Anyway, the factfulness talks about both about his UN data and the story that he told with it, and also about principles for telling effective data stories. And this is Hans's slide. This is what he says in the book is that humans have 10 dramatic instincts that impact their ability to use data effectively. Up in the left corner here is the people tend to go to extremal points, and then there are 9 others. But what I want to point out is this one here. This is he called this one single, but this one is another name for confirmation bias. This is a bias we have where we find a hypothesis we believe, and then we gather up confirming evidence for that hypothesis. And the interesting thing about confirmation bias is the smarter you are, the more able you are to confirm your whatever bias you have. So Hans has this really nice way of describing how to deal with these various dramatic instincts, locate the middle for this, or explore multiple hypotheses. He called that multiple tools to be able to protect yourself from confirmation bias. Now, this is me rather than Hans, but this is my way of taking Hans and saying that data stories in particular include a bunch of logical steps. So there's a setup of whatever story you're trying to tell. Then you take your audience through a sequence of logical steps involving data to some sort of finding or conclusion based on that. And what I'm going to do here is I'm going to briefly demo how animation can be really useful for understanding those logical steps. Animation can make the steps visceral, i.e. wake up the audience. So I'm hoping to wake you up with my demo that's about to come. It can show what changed or stayed the same. And you can also, of course, illustrate the steps in the logic. But what I will tell you for data stories is that words are still necessary. They establish the context, then you can show the animation, and then you can repeat what it's saying. So now I'm going to go to Tableau, and I'm going to show you a data story about the relationship between the bird strike data that you've already seen and migration. This is the FAA data. I already introduced that, so I don't need to do it again. Here's the reports, a number of strikes. You've seen this data already. You can immediately see that migration might be relevant by changing the aggregation from year to month. And you can see that the animation makes that logical step very easy for you to follow along. Now to really see the impacts of migration, I'm going to reorganize this data to put all the January starting at the beginning. And you can see how the animation helps with that. And even though there's a lot of lines here for a lot of different years, you can see there's something interesting going on between May and June. And in fact, if you combine all the years together, then you can very clearly see something is going on between May and June. So I want you to focus in on May and June. And it turns out that birds migrate at altitude. So what I'm going to do is I'm going to take this line and separate out all the strikes that have been reported above 1,000 feet. And that's the orange line here. And you can see that this orange line has 2 bumps. And so this is birds migrate in one direction in the spring, and then they migrate in the other direction in the fall. Interestingly enough, you can see that there's probably still a little migration data in both the less than 1,000 feet and also in where we didn't know the elevation. So this is very common for pilot entered data. For human entered data, there's errors in it. So why do we care about migration? I apologize for, I'm a very crude data storyteller. Think of this as Mount Rainier, which is about 14,000 feet. And I've taken the number of bird strikes and binned it by their elevation height. As you can see, most of the bird strikes are below 1,000 feet, but there are bird strikes for each of the bins above 1,000 feet. And what I'm going to do is shift from the number to the average cost. And as you can see, the bird strikes at altitude on average are much more costly. And that's why we should care about the bird strikes. This was me showing the power of sort for being able to understand data. And then this is the final part of the story. This, by the way, is the miracle on the Hudson. As you can see, it was an outlier both at altitude and also an extremely expensive strike. Looks like I might be running out of time. So let me get out of there. Let me go back to my talk. But I'm going to be done pretty quickly here. So, so we might have time for a question or two. So that was the animation demo. So now I want to just quickly dive into the big problems that I started at the top. Just one of them, the climate crisis. In particular, I'm going to point you to David Attenborough's recent film, Life on Our Planet. Fabulous film. It's actually pretty optimistic in some ways, although the data in it is pretty dire. What I did as part of the prep for this talk is I went around on my own and found out that there was such a thing as conservation drones. In other words, drone technology can be used to gather up data. The first thing you have to do on big problems is gather data. And so this is a drone looking at an osprey nest on top of a telephone pole, and those are the people flying the drone down at the bottom. Another example of gathering up data that is much more recent from Washington State, where I live, was there are these things called murder hornets. This is a murder hornet. You get a sense for how big they are. They're called murder hornets because they kill honeybees, and they're very effective at it. And what you're seeing here is a picture of a University of Washington graduate student who is using dental floss to put a little sensor on this murder hornet, and they were able to then track the murder hornet as it flew around. Here's the murder hornet on an apple tree with the sensor attached, and they were able to track the murder hornet back to a nest where they were then able to trap the entire hive inside the nest and deal with it. And one of the nasty things about murder hornets is that they have a lot of queens. So you really want to stem the nest while you can. But the view I have is that, first of all, there's going to be a lot of analytical conversations with data that we're acquiring from the world. And this is also going to be, climate crisis is going to be a source of jobs because you have to not only analyze and understand the data and then talk to each other about the data, but then you need to take the data back out into the world because we've meddled with the climate everywhere, and we need to do that. So thank you very much for your attention. I'm willing. Oh no, I actually have a meeting in just a couple of minutes, so I can't stay long. But if there are any quick questions I can answer, I will.
Great, thank you very much, Jock. I'm looking. Laura, I don't see any questions yet. Is that just me?
No, yeah, there aren't any questions that I can see.
Well, since I filled up the time, I don't feel bad about it. But Mark knows how to reach out to me if somebody has a question after the fact. So.
Oh, there's just one question right now from Christina. She's just asking, how easy is it to combine multiple and incomplete data sets?
So that's a fabulous question. To combine data sets down at the row level requires data skills, and you probably want to know what it means to join data together. But combining data is actually very common. It is like we call that converging lines of evidence. And you take a bunch of incomplete data and you converge it together, and then you can actually, you know, get to something where you might have high confidence in your conclusion. You might even call it a truth. And so converging incomplete data together is in fact a really big part of dealing with data, and all data sets are incomplete. And the final thing I'll say on that one is it's not just quantitative data, it's also qualitative data, text. There's all kinds of data out there that needs to be converged together. So anyway.
Jock, you got another question from Anton, and this one's about limitations of human short-term memory and whether Tableau takes that into account in any way.
Well, so by putting the data out in the physical world, we're providing a way for people to deal with their short-term memory, but only with that. That's only tactics. We're not actively dealing with, not modeling people's short-term memory. 7 ± 2. It's really a very daunting limitation of human brains. So,
okay, and then we have a question from Yinan. How do you deal with inaccurate raw data, and you know, ensure that the data is correct?
Well, that's a huge topic, but yes, by visually encoding it, you can then make the process of cleaning it up, yes, getting from raw data to clean data tables is a major undertaking. And of course, to add to it, the amount of data is growing exponentially, which means that there are performance issues as well. So,
okay, and one last question. This one's a complicated question from Paul Milgram, of course, and it's asking, do your domain-specific languages have any means for automated warping of data? For example, imposing interdata distances onto categorical data, perhaps by means of lexical analysis.
No, but that is a possibility that you can do on top. One of the features that got added to Tableau over the year was to take temporal data and densify it a little bit so that you could deal with it. But the actual warping, I think, is still a research problem. So,
great. Okay, and the last thing I'll mention is that Jock's available this evening. He's giving a talk at Tokai at 7.
Same talk.
Sorry?
Same talk.
It's yes, but there'll be a bunch of HCI and UX people there, and there'll be half an hour for questions. So if you want more questioning, there'll be more time then.
And maybe if it's possible, would you be able to just put your email within the chat box if students are interested in contacting you for further questions?
Yeah, also I will do it now.
Also, we got one more comment. Thank you for not blaming Canada geese for the bird strikes.
That was also Paul. Anyway, so I put my email in the chat box. So anybody chat me if they want the information on how to attend the session this evening. And thank you so much, Jock. I think it was a really interesting talk, and I've heard it twice now, and I'm going to hear it again tonight, and it still stays endlessly interesting.
Awesome, good. I hope sometime to come visit Toronto post-pandemic. Lots of good restaurants there. So.
Yeah, we would love to see you. Great. We look forward to it.
Thank you so much.
Yeah. Okay. Thank you very much.
Bye. I'm off to my next one.
Yeah. Bye.